At the end of this video, you'll be able to create your very own CRUD application with Rust. We will be using the Axum framework and Postgres for our database. The repository for the source code of this project will be linked in the pinned comment below. In your terminal, create a new Rust project by typing cargo.toml followed by your project name. Next, cd into your project directory and open with your favorite editor. From the command line or Postgres admin, create a Postgres user and database for this project. I will name both the user and the database Axum Postgres, and the password of the user will also be the same. Now log into your newly created database and create a tax table, which will contain a tax ID column, name and priority. If you use Linux or macOS and you have trouble setting or logging into your Postgres database, be sure to confirm that your pghba config file you have your authentication set to MD5 for all users, but you can leave it at pair for your Postgres user. By default, Rust uses 4 spaces for a tab indentation. To switch to 2 spaces, we create a rust fmt.toml file and specify the tab spaces to be 2. The cargo.toml file in your project directory contains a list of dependencies we'll make use of in your project. To run our backend service, we'll need 2 main dependencies, Axum and Tokyo for the runtime. SQLX is a crate for validating and running our SQL queries. Since we are using SQLS for the Postgres database, we add Postgres in the features arrays. We will use Tokyo as our runtime and a native TLS. We want our SQL queries to be checked at compile time. The macros that run these don't come by default, which makes us add macros in the features arrays to enable this. An important crate to use is cd and cd.json, which helps in serializing and deserializing Rust structs. Whenever we wish to send and receive JSON, this will require the drive feature from cd, so we specify by adding it in the features array. Our last dependency is .env. This helps in loading variables from the .env file, which we will create in the project's root to the program's environment variable. The .env file we created will contain 2 variables, our database URL, which is the Postgres connection string of our database, and server address, which is the host and port we wish to run the server on. The database connection string is formed using the following. First, we write Postgres followed by a colon and double slash. Next, we input the user, a colon and then the password, followed by an @ sign and the address of our Postgres database, a slash and the Postgres name. We can now get into writing our Rust codes from here. In the main.rs file, first, we bring in the structs, traits, functions and macros, which we'll make use of into our program scope. So with the use keyword, from Axum, we get the path and state struct from the extract modulo, the status code enum from HTTP, the get and patch function from the routing modulo, and lastly the JSON and the router structs. From cd, we will get the serialized and deserialized traits, and from cd.json we expose the JSON macro, which will be used to create the JSON we send to the user. In SQLS, we expose the pgpool and pgpool options, which are type aliases for pool and pool option structs, specialized for Postgres. And lastly, we get the TCP listener from Tokyo. Every entry point in a Rust binary is a main function. Here, our main function will be asynchronous and with an attribute macro called main from Tokyo. The 6 steps we'll take to create our service is to first expose the environment variables from the .env file, create program variables from the .env file, create a database pool, create a TCP listener, compose the routes and serve the application. To expose our environment variables from the .env file into the program, we achieve this by calling the .env function from the .env crate. This returns a result enum which errors if it can't access the .env file. When that happens, we want to stop the application and print the error message. We do that by calling the expect method on the results enum. The environment variables can now be accessed by the var function from the standard library when we pass in the variable name in its argument. We can now create a server address and database URL variable in our program, and their values will be gotten from their respective environment variables. If there are no server address, we assign a fallback value. But as for the database URL, if it doesn't exist, we stop the program with an error message. To create a database pool, initialize a pool option struct. Specify the number of maximum connection and connect to the database. The connection is asynchronous and return a result enum, so we need to await it, and if it errors, we stop the application and print an error message. Next, we create a TCP listener simply by calling the bind method from the TCP listener with the server address. Await it, and if it errors, we close and print the error message. If successful, we print a message to the console with the address our API is running on. The routes for our REST API can now be composed. First, create a router struct and add a route for the home part. For start, we accept a get method and return a hello world string when we receive a get request from the home route. We assign the route struct to a variable and go ahead and serve the application and test if the setup is successful. We call the serve function from Axum and pass in the TCP listener and the route struct. Await it, and if there is an error, we close the application with a message. When we test the API on Postman, we get a hello world response and our setup was successful. Now we create the routes for getting, creating, updating and deleting tasks. We get and create tasks from the /task route, but to update and delete, we need the task ID of that specific task, so we add a task ID parameter. Each of the handlers needs to access the Postgres pool. Hence, we add the DB pool in the route state, and each handler can be able to access it. The get, create, update and delete task handler will all be asynchronous. Get the DB pool from the state and return a result enum whose OK and error value is a status code and string tuple. For the get task handler, we need to fetch task from the Postgres task table. We will do this using SQLX, but first we specify the type the rows fetched from our query will look like. So outside the get task function, we create a struct called task row. The task row struct will have a task ID as i32, and since the priority column is an integer but can be null, it should be an optional i32. The task row struct also needs to be serialized to JSON before sending as a response. Therefore, we need the serialized trait from sede. To get the rows from Postgres, we call the query as macro from SQLX. Passing the struct, the rows will be cast to, followed by our SQL query. We select all rows from the task table and order them by their IDs. We then call the fetchAll method and pass in the database pool in its argument. Await the result, and if it errors, we map the error to a tuple that contains a status code enum with an internal server error element and a string of a JSON value, whose fields are success with a false value and a message whose value is the error string. We then return the mapped error early, but if there is no error, we assign the task rows to a variable named rows. Lastly, we return an OK value that contains a tuple which contains an OK status code together with a JSON string that contains a truthy success field and a data field that contains the task rows. To create a task, we will need to receive a JSON from the request. This will require us to create a struct in which the JSON from the request body will be extracted. Our create task request struct will have a name field which is a string and a priority which will be an optional 32-bit integer. The JSON from the request will be deserialized into this struct, so we drive the deserialized trait from sede to enable this. So in the create task handler, we extract the JSON from the request body by adding this in the function parameters. Since the JSON is extracted from the request body, it needs to be the last parameter, as any extractor that consumes the body should be the last parameter in an Axum handler. You can read more about this in its docs. The link can be found in the pinned comment. When we create a row in the task table, we will need to return the task ID of the created task and add it to the response. So just as in the get task, we create a struct that describes the row we return from the SQL query. Since we will need to return just the task ID from the row, the create task row struct will only contain a task ID field of type i32. This will also drive the serialized trait from sede, as it will be serialized to JSON and added in our response. In the create task function, we will then call the query as macro from SQLX, pass in the create task row and the SQL query for inserting the task. In our SQL query, we add the name and the priority of the task and return the task ID of the task created. Looking at the query, we can see a $1 and $2. This is where the task name and the priority we pass in the next argument are added when SQLX prepares this query. The task.name and task.priority are gotten from the task extracted from the JSON in the request body. Since we only return one row from the query, we will call the fetchOne method and pass in the database pool in its argument, await the result, and if it errors, just as in the get task, we map this to a tuple that contains a status code enum with the internal server error value, and a string of a JSON value, whose fields are a success with a false value and a message whose value is an error string. We return the mapped error LA, but if there is no error, we assign the returned row to a variable named row. Recall that in the update and delete task route, we specified a task ID parameter in each path. We need to extract this path in the request, so we make use of the path extractor from Axum, and since the task ID are integers, we use an i32 as a path type in the extractor. For updating a task, we will need to send a JSON in the request that contains the fields we want to update. Therefore, we create a struct that describes the JSON type. This will contain a name field which is an optional string and a priority field which is an optional 32-bit integer. They are both optional since we may need to update only one of the given fields and the other needs not to be specified. Just as in the create task request struct, we drive the serialized trait for the struct and we can now extract from the request. So in the last parameter of the update task handler, we extract the JSON as the update task request struct. For updating a task, we don't need to return any row from Postgres, so we can just use the query macro from SQLX and pass in the SQL query we will use in updating the task. In the update query, we can see that we have some Postgres parameter $2, $3 and $1 for the name, priority and tax ID values. Therefore, in the next argument, we pass in the tax ID from the path first, followed by a tax name and priority from the JSON. Since we aren't returning any row, we call the execute method and pass in the database pool in its argument. Await the result. Whenever it errors, we map the result as usual and return early. If our query is successful, we return an OK value with the usual tuple, but in the JSON string, we return just the success field. The update query we just used isn't the best for some reasons, which we shall see later on, but let's move over to the delete task handler for now. Just as in updating task, when deleting task, we don't need to return any data from the query. Therefore, we call the query macro from SQLX and pass in the delete query. In our delete query, we only used one parameter, which is the task ID. So we pass in the task ID from the path in the next argument. We then follow the same procedure from the update task handler, which is to call the execute method, await the result, map the error and return early if it does error. If this is successful, we return an OK value with the usual tuple, and the JSON string will contain just the success field with a truthy value. Now to test our API. On Postman, we send 3 post requests to create tasks, and we see that they are all successful. We then test the get request, and we can see all 3 tasks. We delete one with the API, and when we rerun the get request, we just have 2 tasks left. Let's try to update the task with the task ID 1. We update the name to study and priority to 4, and when we fetch the task, we can see it's updated. If we try to update just the name field of the task, it is successful, and when we fetch the task, we see that the priority becomes null, since SQLX takes a non-option enum as null in Postgres. And when we try to update just the priority, we get this error, since the name column cannot be null according to our specification. To resolve this, we create our SQL query dynamically at runtime to update only the fields we specify in the JSON request body. So if you want to update just the name, our SQL query will look like this. For priority, it will look like this, and for both, it will look like this. While examining these 3 queries, we can see that our dynamic query will begin with update task, set, and ends with where task ID equals $1. A challenge we'll face is the commas in between the fields we need to update. If there are no fields specified in the JSON, our query has no fields to update, which will throw our error when we run. To solve this, we update the task ID field to itself, making the query always contain a field, and we can add a comma and the other fields we wish to update. The code to build our query in this form will look like this. Next, we dynamically add the parameters of the Postgres query. From SQLX, we call the query function and not the macro this time, since compile time checking won't be suitable in this situation. To add the task ID parameter, we call the bind method and pass in its argument. We assign this to a mutable variable s, and if the task name is some value, we add this parameter by calling the bind method on s and assigning it to itself. We do the same for the priority. Now we can call the execute method on s while passing the database pool in its argument. Await the result, map the error value as usual and return early if it does. We can return an OK value with our usual tuple if the query is successful. We can now update a single field in the task record without affecting other rows. If you enjoyed this video, please support me by giving me a like and subscribe for more videos. If you have some questions, you can let me know in the comments. Links and references used in this video can be found down below in the description and also in the pinned comment.